Hi guys, in this video we are going to discuss the concept of hydrogen bonding, which is a very important classification of intermolecular forces. Now, as we saw previously, hydrogen bonding, we're actually going to build upon the concept that we talked about previously, namely this idea of a dipole-dipole interaction, and we're going to see how hydrogen bonding has a lot of the same properties of a dipole-dipole interaction, but with some very important differences or enhancements. And we're going to really go into the detailed anatomy of what a hydrogen bond is in this little mini lecture, and we're going to see some of the very important consequences of this special type of bonding. So first up, the definition of a hydrogen bond. So a hydrogen bond is defined as a special type of dipole-dipole attraction. Okay, so it's still dipole-dipole. It's a special type that results when you have a hydrogen atom that's bound covalently to a strongly electronegative atom, right? And typically the strongly electronegative atom will be either nitrogen, oxygen, or fluorine, right? And if you have this strongly electronegative atom bound to a hydrogen and then another strongly electronegative atom in close proximity, then, and that atom has a lone pair of electrons, you have the opportunity for forming a covalent, or a hydrogen bond rather. And we'll see some pictures of what this is, right? But before we take a look at those pictures, I want to first show you some of the evidence for the existence of this special type of bonding. If we look at this plot down here, at the bottom of the screen, what we're looking at is boiling point, right? As a function of different types of halides, right? So we've got different atoms from the periodic table bound to hydrogen atoms, and we're looking at the boiling point of these different substances. Now I want you to think about what goes into the process of actually boiling a substance. And we're going to talk about this in more detail a bit later on in the course. But simply put, if you want to boil a substance, right, then you are going to be taking that substance that's in a liquid phase and breaking apart the interactions that are holding those molecules together in order to get those molecules to move into the gas phase. In other words, you're going to have to put energy in order to break those intermolecular interactions. Okay, so the higher the boiling point, the more energy you need to put in order to break those bonds. In other words, the higher the boiling point, the stronger the bonding interactions between those atoms. Okay, and so there's a couple trends here that I really want to draw your attention to in this figure. First off, I'm going to highlight these strongly electronegative elements that we referenced in our definition of a hydrogen bond: oxygen, fluorine, nitrogen. Okay, and what we're looking at here is a variety of different halides that can form that have similar geometries to one of these oxygen, fluorine, or nitrogen containing compounds. So for example, we could go across the periodic table and look at water, H2O, hydrogen sulfide, H2S, H2SE, H2TE, tellurium, right? And what we see is that when you have one of these strong electronegative elements, the resulting boiling point is significantly higher than the rest of those compounds in that series of halides. Okay? In other words, the presence of the strong electronegative compound is doing something to dramatically increase the strength of interactions between the molecules. Okay? And the term that we use to describe this enhanced strength is called the hydrogen bond. Okay? So the hydrogen bond is responsible for these elevated boiling points. All right. So armed with that empirical evidence here, then our next task is to basically try and understand and rationalize this very interesting behavior using what we know about quantum mechanics. Okay, so we're going to go back to our discussion of molecular bonding theory and thinking about what is it that makes up a bond, what is it that makes up a lone pair. Okay, so first note, we need to remember that electron pairs reside in orbitals. So if you have ammonia, then that means you're going to have two little electrons drawn by the little dots right here. representing one lone pair. On water, you're going to have 4 little dots here, 2 lone pairs, right? 3 lone pairs on fluorine, so on and so forth. Okay. Now, using what we just talked about in the context of dipole-dipole interactions, if we look closely at, for example, the oxygen-hydrogen bond, what we see is the presence of a very strong dipole moment, right? A dipole moment with a positive charge, or positive end, partial positive end on the hydrogen side, negative end on that oxygen side. All right, so if we just start off by orienting these 2 water molecules to describe their intermolecular interactions in terms of a simple dipole-dipole model, we'd come up with something like this, where we get this head-to-tail arrangement of the 2 dipole moments. Okay, great. And this would, of course, account for an added strength on the interaction, depending on the strength of these dipole-dipole terms. Okay, now the interesting thing that happens in the context of a hydrogen bond, really relies on a very important concept from quantum mechanics, this idea of orbital overlap. Okay, so remember when we were just trying to describe quantum mechanically the idea of a covalent bond, we said, well, you need an overlap of orbitals. So overlapping orbitals with the electrons residing in those overlapping orbitals accounts for bonding interactions. Okay, so then what ends up happening here in a hydrogen bond is that that orbital that has these 2 unpaired electrons is going to be attracted to that hydrogen atom that has a partial positive charge, and it's going to be so attracted that you will actually start to see a significant degree of orbital overlap. So you start seeing the formation of almost an extended bonding, right, over this whole region. So hydrogen bonds, it's like a dipole-dipole interaction with a little bit of covalent character, right? That would be perhaps be the best way to sum up the hydrogen bond from a technical perspective. Okay, so I'll say that one more time. So from a technical perspective, you can look at a hydrogen bond as a dipole-dipole interaction with a tiny percentage of covalent character. We're actually getting a little bit of orbital overlap of the lone pair electrons wanting to come up and grab, get closer to that hydrogen nucleus. Okay, now, simply put, right, you can think of the hydrogen bond as essentially an electrostatic sandwich, right, where you have on one end an electronegative atom, remember it can be oxygen, nitrogen, or fluorine, right? On the other end, you have another electronegative atom, oxygen, nitrogen, fluorine, right? And sandwiched in between is our little hydrogen atom, okay? So you want to think of those electronegative elements as sort of the bread in your sandwich. Oxygen, nitrogen, fluorine is the bread, and hydrogen is the cheese or meat, or depending on what you want to put inside your sandwich there, right? So basically, this little model here, this electrostatic sandwich model, is what you always have to be looking for when you're trying to assess the types of intermolecular interactions that can occur within a given compound. Okay, dipole-dipole, identify, do you have polar bonds? But you always have to take it a step further and ask yourself, can you have this specific type of dipole-dipole interaction? Can you get this hydrogen bond electrostatic sandwich, right? Because if you can, what our plot showed is that it can have a very dramatic impact on the strength of interactions. And I really can't overstate the importance of hydrogen bonding, and we'll look at more examples of hydrogen bonding in this class and when you get into your biology classes and future classes. For right now, I want to list off a handful of very important phenomena that are strongly dependent upon hydrogen bonding. So first off, the idea of surface tension, right? When you have, so for example, beaded water on a surface, the tendency of water molecules that stick very closely to one another because they can engage in this hydrogen bonding interactions, right, results in this sort of beating up or bubbling, or the formation of a drop of liquid. Okay, it's that liquid trying to stay close and bound to its other neighboring molecules. Crystal structure, right? If you look at the extended three-dimensional lattice of a crystal, we find that the interactions involved in a lot of these different molecules are in fact hydrogen bonding interactions, or play a very prominent role. Of course, they're not the only force at play, but they are a very strong contributor to that crystal structure. And one structure that we talked about previously is the structure of DNA, and actually hydrogen bonding is what's responsible for the fidelity of and this idea of complementarity in DNA, right, and the DNA replication process. So when we're looking at DNA molecules, many of you guys know you have this double-stranded molecule, and you find this relationship where if you have on one strand a T, you're always going to find an A in the homologous position on the other strand, on the second strand. Okay. Similarly, if you have a C, if you have a G, you'll always see a C, and of course vice versa. Okay. And this it's called complementary base pairing that gives rise to this very specific structure in the DNA molecule. And this complementary base pairing is the result of none other than hydrogen bonding interactions. Okay? And of course, hydrogen bonding goes to other biomolecules as well, protein structures, whether they're proteins floating around in solution or in in cell membranes and all that fun stuff. Literally, hydrogen bonding is everywhere. So to put hydrogen bonding in perspective here, from an energetic standpoint, it's going to lie somewhere in between dipole-dipole and charge-charge interactions. So again, proximate values here, 20 to 40 kilojoules per mole. So it is stronger than the typical dipole-dipole for the reasons we've discussed in this lecture, but not as strong as those charge-charge interactions. Okay, so we can round out our discussion here with a simple example where we're going to be asked to determine the dominant intermolecular force for a set of compounds and then use that to predict the relative boiling points. So in this example, I'm giving you sodium chloride, water, and formaldehyde, and we want to be able to look at these structures, predict which intermolecular force is going to be dominant, right? In other words, the strongest intermolecular force present. And then we're going to say, well, depending on who has the strongest intermolecular force, we're going to predict who's going to have the highest boiling point. Okay, so let's go through starting from the left to right. Sodium chloride. Well, of course, we know sodium chloride has, it's built from these positive and negatively charged ions. So the strongest interaction in sodium chloride crystals is going to be charge-charge. Water molecules, as we just saw, are able to undergo hydrogen bonding. And now with formaldehyde, if we look at the structure of formaldehyde, right, we want to ask ourselves, well, what intermolecular forces are present? Certainly, there's going to be a dipole moment. So there's certainly going to be dipole-dipole, but we want to ask ourselves, are there going to be stronger interactions? Well, of course, there's no charge. There's no net charge, so there's no charge-charge interactions. But we need to ask ourselves, is there a possibility of hydrogen bonding? Now look, this molecule does not have a hydrogen bound to one of these strongly electronegative atoms, oxygen, nitrogen, or fluorine, right? The only one that's present is oxygen, and it does not have a bound hydrogen. Because there's no hydrogen directly bound covalently to an oxygen, nitrogen, or fluorine, you can't have hydrogen bonding. As a result, the strongest interaction here is going to be our dipole-dipole interactions for formaldehyde here. And so as a result, the boiling point are going to be ranked such that sodium chloride is going to have a higher boiling point than water, which is going to have a higher boiling point than formaldehyde. And in fact, you would see this, that, at room temperature here, the sodium chloride is going to sit there on the table salt. Water is going to melt, it's going to become a liquid, and formaldehyde will actually become a gas. Okay, so with that little example here, we're ready to move into our final intermolecular force, which is called the London dispersion force.